Hello, everyone from the HL class. First thing is to wish you all good health and the same for your loved ones. I miss you all very much. And this is going to be the first of two videos that I'll be sending you out for this week. So, the first thing I want you to see is what topics we have covered from the program so far. So, notice that the first topic in the program, in the IB program for HL, is algebra and function basics, which we have done, equations, definition of a function, composite functions, inverse functions, and transformations of functions. In the topic of functions, subtopics of that are polynomial functions, quadratic functions, zeros, factors and remainders, rational functions, solving equations and inequalities, and partial fractions. In sequences and sequences, arithmetic sequences, geometric sequences, series, the binomial theorem, and the hated counting principles. We also covered exponential and logarithmic functions, exponential functions, growth and decay, Euler's number, logarithmic, exponential, and logarithmic equations. Proofs, basic laws and simple proof, direct proofs. Indirect proofs is something that we haven't done, and it was added to the content this year. So you might want to go to chapter 5 and review proofs. Mathematical induction. We've also done trigonometric functions and equations, angles, circles, a unit circle, graphs of trigonometric functions, trigonometric equations, identities, and inverse trigonometric functions. From geometry and trigonometry, measurements in 3 dimensions, right-angled, triangles, trigonometric functions of acute angles, trigonometric functions of any angle, the sine and cosine rule. We also covered complex numbers, the complex plane, powers and roots of complex numbers. And then there is chapter 9, which we're not going to cover in this long distance education period. We're going to wait until August to cover lines and planes and vectors, lines in space, planes, and all this stuff about vectors, lines, and planes. Statistics we're also going to cover in August because a lot of you have not yet seen it, and I think it's better if we do this when we are together, physically present together. Probability, which is something that a lot of you hate. Also, we will be covering that once we get back to school, hopefully in August. What we will continue with, and which will be the topic of this video, is differential calculus. And we're going to start talking today about limits of functions. So that's going to be the topic of this video. But let's keep going, keep scrolling down so you guys see what other content we would have to cover this coming year. So hopefully we will be able to cover differential calculus 1, derivatives, maxima and minima, tangents and normals. Then we would do differential calculus 2, derivatives of composite functions, products and quotients, derivatives of trigonometric and exponential functions, implicit differentiation, logarithmic functions and inverse trigonometric functions, related rates, optimization, and L'Hopital's rule. So that's what I hope to cover in these weeks that we have till the end of this course. For next year, we would continue with integral calculus 1, integral calculus 2, and probability distributions as well. Random variables, the binomial distribution, continuous distributions, etc., etc. But I think it makes more sense for us to continue right now. This would be the last thing in all talk. So there's 16 different topics, and we're a pretty good point right now because we would be covering our 8th and 9th topic, hopefully, for this course, for this year. So as you can see, we're in a pretty good spot with regard to how much we have covered. And this is just to give you an idea of where we're headed and where we're at the moment. So without further ado, let's begin then today with the video on limits of functions. So the topic we're going to be working on, you can find in Chapter 12, Differential Calculus 1. And the first thing we're going to talk about is limits. Before that, we need to talk about the learning objectives within this concept, and by the end of the chapter, you should be familiar with these different topics. The concept of limit is something we have to cover. The derivative is a gradient or slope function and as a rate of change. Finding the derivative of a function with the definition of limit. Finding the derivative of polynomial functions. Finding the derivatives of sine and cosine of x. The relationship between the graph of a function, its first derivative and second derivative. Identifying where a function is decreasing or increasing. Finding and testing maximum, minimum, and inflection points of graphs. Kinematic problems involving displacement, velocity, and acceleration. Those of you who are in physics are pretty familiar with this. And finding the equation of a tangent or a normal at a given point. So on this first slide, we're going to analyze a couple of graphs. So if you look at the graph on the left, figure 12.2, it refers to an average velocity from a distance time graph. So the blue line that you see, or the function, is the motion of a particle. And the y-axis represents the distance that the particle incurred in. And the x-axis is, or the t-axis, is going to represent the time in seconds. So if you are asked to find an average velocity of that particle within a time frame, it's a pretty simple operation. How so? Well, if you take the coordinate at 4 seconds, so at 4 seconds, we can see that the distance was 2, and then at 10 seconds, the distance was 4,25 meters, or 4.25 meters. Then we can find an average velocity, because velocity is distance divided by time, or difference in distance divided by difference in time. So we can see here that the average velocity from t equals 4 to t equals 10 seconds would equal to the difference in distance over the difference in time. And then we subtract those and divide and get 0.375 meters per second. So this is a fairly simple operation. But, and this is where calculus comes in, at least differential calculus, what happens if we want to find the instantaneous velocity? Now, the instantaneous velocity means at this instant. So at 7 seconds, when the distance was 3.875 meters, what was the exact velocity, or what was the instantaneous velocity at that time? So this is a different question, right? Although the first mathematicians to delve in this topic used a very similar approach to the one on the left. So the idea here is to find a very small difference in y and divide it by a very small difference in x. Now notice, if you guys are familiar with this, this is actually the notation that later on would become derivative. So the trick they played for this, or they applied, was this. What happens if we want to use 2 points that are very, very close to each other? So close to each other that their distance is nearly zero. Nearly zero. So think about that situation. Thinking of the line in terms of a function such as f of x, we could say that finding that instantaneous velocity would be the same as finding the limit of a value, let's call it h, as h approaches 0 of, remember that's y2 minus y1. In this case, we can talk about f of x plus a small distance h, almost 0, minus f of x. Regardless of what x is, this would be the difference in y, or the difference in distance. And then what happens if we divide this by the difference in x, which we know is just going to be something very close to 0, h. So this, by the way, is the definition of the derivative. We will go more into this as we advance within this chapter. So here we are with limits of functions. So what is the limit of a function? Let's take a function such as f of x is equal to x squared. Now that's a very familiar function. We all know what it looks like. It's more or less like this. So what happens if they ask us something like, what is the limit of f of x, or x squared? What is the limit of x squared as x approaches 2? So the way to test limits is by approaching the x value from the left and from the right. So what does that mean? Well, that means that when x equals 2, and let's mark it over here. When x equals 2, and we approach it from the right and from the left, what y value does it approach? Now, in this case, it's very easy to see because all we have to do really is plug in 2, and we know that 2 squared is 4. And even if we approach this value from the left, say if we plug in something like 1.9999 or 2.0001, they will give us values that are very close to 4, and that would be the way to prove that the limit as x approaches 2 of x squared is 4. So this is a very simple case which we can use to explain what a limit is. But if we go to example 12.1, and in this case they ask us to find each limit using your graphing display calculator to analyze the behavior of the function. Now, why is that? Now, in this case, in letter A, they're asking us to find the limit of the function as x approaches 0. So if we plug in sine of 0 over 0, this is undefined, right? We know that sine of 0 is 0, and 0 divided by 0 is undefined. So we can't really tell what the limit is just by plugging in 0. The same with B. If we plug in 0 here, we get cosine of 0 minus 1 over 0, and this also is going to give us 0 over 0, which doesn't make any sense. So what we have to do is analyze the behavior of these functions by studying the graph, and that's what we're going to do. So here we have the solution to letter A. And as we said before, when x equals 0, we're not really able to evaluate the limit by direct substitution because we get this and it's undefined. But if we look at the graph here, notice that although this function, sine of x over x, becomes undefined at 0, we can see that if we approach 0 from the left, as well as if we approach it from the right, we can see that 0 tends to 1. Therefore, we can say then that the limit of sine of x over x as x approaches 0 is equal to 1. And this is something very useful that we are going to need later when we do limits with trigonometric functions. So now for part B, as we did with sine of x over x, if we plug in 0 and cosine of x minus 1 over x, it will be undefined, right? But if we look at the graph, what happens as x approaches 0? Well, you can see it right here. The function tends to 0, right? So we can say then that the limit of cosine of x minus 1 over x as x approaches 0 is 0. And this is also another important limit that we will need to solve problems with trigonometric limits. So here we are with example 12.2, and they ask us to find the limit as x approaches 0 of 1 over x squared if it exists. That's a hint already. But before we do example 12.2, let's look at this important definition, because this is the official definition of what a limit is. So if f of x becomes arbitrarily close to a unique finite number L as x approaches c from either side, then the limit of f of x as x approaches c is L. The notation for indicating this is this. So this is basically a formal way of defining what we did in the previous examples. So when a function f of x becomes arbitrarily close to a finite number L, we say that f of x converges to L. So let's now go to the solution of example 12.2. And let's take a look at the graph. So if we study the graph, we can see that as x approaches 0 from the left, you can see that the graph of f of x tends to infinity. And the same thing as you approach 0, as x approaches 0 from the right, it also tends to infinity. And that's easy to see because if you divide 1 by numbers that are very, very close to 0 squared, you'll always get a positive, and you'll always get very, very large numbers. So taking this into account, because it doesn't converge to a value L, then we can conclude that the limit of 1 over x squared as x approaches 0 does not exist. So what we have on the next slide is a summary of the properties of limits. So they start by saying, let a and b be real numbers, let f and g be functions with the limits. Limit of f of x as x approaches a equals L, and limit of g of x as x approaches a is k. And then here come the definitions or the properties. So the constant property, that means that if b is just a constant, then the limit as x approaches a of b is just b. Then you have the property of a scalar multiple. If you're trying to find the limit of a function as x approaches a, in this case is limit of f of x, then that would equal whatever f of x converges to, which is L, times b, the constant. Then you have the property of sum or difference, which says that if you're doing the limit as x approaches a of f of x plus or minus g of x, you can find those limits independently and then add them or subtract them accordingly. And the same can be done for the product and the quotient, where you can find these limits separately and then just multiply them or divide them. Now, why is this important? Because we're going to need these properties in order to solve limits using algebraic properties. So here we are with example 12.3, and they ask us to evaluate each limit algebraically. Now we're going to do them one by one. So let's start with letter A. So what is the limit as x tends to infinity of 5x minus 3 over x? Now, one of the things that we want to do with these limits is rearrange them, and this one's pretty easy to rearrange. Normally, you have to be careful with using the notation, so don't forget to write limit as x approaches infinity. And then let's rewrite this as 5x over x minus 3 over x. And then we can use the properties of limits to say that this is the same as the limit as x approaches infinity of 5x over x minus the limit as x approaches infinity of 3 over x. Now, take a look at this first one, because x divided by x is 1, and this is going to end up being a constant. So this limit will equal 5. And then when we look at this other limit, what happens with 3 as you divide it by larger and larger and larger numbers. This tends to 0. So this would be 5 minus 0, which is 5. For letter B, they ask us to find the limit as p approaches 0. So in this case, it's not x. We just have to be careful with that. So here's one p, and here's the other p. Now in this case, I think the easiest thing to do is to simply plug in 0. So we can say that the limit as p approaches 0. Now notice the notation. You have to use a parenthesis here. 3x squared minus 4px plus p squared. And let's just plug that in, but don't forget to rewrite limit. So limit as p approaches 0 of 3x squared minus 4 times 0x plus 0 squared. So this would equal simply 3x squared because this is 0 and so is this. So here we are now on part C. And this is the limit they ask us to find, and this is as h tends to 0. Now, but notice we can't really plug in 0 because if we plug in 0 here, then this would become undefined. So what we need to do is to expand and see if we can simplify this expression. So let's rewrite this as limit as h approaches 0 of this expression. So let's expand this. So we're going to get x squared plus 2xh plus h squared minus 6 minus x squared plus 6 squared. Let's rewrite it like that. Plus 6, not 6 squared. Okay, plus 6. And all of this over h. So what we need to do is find a way to cancel h. And I think we can see here that h will be canceled out because x squared minus x squared cancels out, and negative 6 plus 6 would also cancel out. So we end up with this expression. Now don't forget to rewrite this limit thing because it'll cost you points if you don't. So limit as h approaches 0 of 2xh plus h squared over h, and then let's factor out h on the top. So rewrite, always write this. Limit as h approaches 0 of h times 2x plus h over h. So now we can cancel out the h's and we can solve for this. So notice that all we have to do is plug in 0 for h, and that would just give us 2x plus 0. Therefore, the answer for this would be 2x. Now later on, you're going to understand that all we really did was find the derivative of x squared minus 6. But that's a topic for a future video. So here we are now on question D, and they ask us to find the limit as x approaches infinity of the function 3x squared minus 5 minus 1. I think they're missing an x here, 5x minus 1 over 2x squared plus 1. Now, I don't know if you guys recall, but when we were doing horizontal asymptotes for graphing, I told you guys that if we use limits to infinity, we could find the horizontal asymptotes of these rational functions. And the deal was, or the rule was, that if you had x's with the same exponent, then all you had to do was really grab the coefficients of those x's that had the highest degree and were the same. So this will simply equal 3/2. Now, unfortunately, this is not how we're going to do this because they are asking us to do it algebraically. So I'm going to show you guys how to do it algebraically. So if we do this algebraically, what you do is that you use a very simple trick. So you go limit as x approaches infinity, and we can rewrite this and divide everything by x squared. So we would get 3x squared over x squared minus 5x over x squared minus 1 over x squared. And all of this divided by 2x squared over x squared plus 1 over x squared. So then this would equal, and this is where we can apply the properties of limits. First of all, we're going to cancel out these terms because x squared over x squared can cancel out, x squared over x squared can cancel out, and this x can cancel out with one of these x's. So let's rewrite this using the properties of limits. So we can rewrite this as limit as x approaches infinity of 3 minus the limit as x approaches infinity of 5 over x minus the limit as x approaches infinity of 1 over x squared, and all of this divided by the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x squared. And then this would simply equal, this is where we use the properties of limits, right? So this would equal 3 minus 0 over 2 plus 0. And this evidently is the same as 3/2. Very well, so here we are now on example 12.4. And in part A, they ask us to estimate the value of the limit as x approaches 0 of square root of x squared plus 4 minus 2 over x squared by evaluating the function for these values here. Now notice that all of these are different approximations to 0 and increasingly close to 0, as you can see, 0.1, 0.01, 0.001, etc. And they do a plus minus, meaning do it from the left and do it from the right. Although in this case, it doesn't really make a difference because x is squared. That means that this is always going to be greater than 0. So really, we only have to plug in the positive values. So you guys can do that with your calculators. And you can see a pattern that I'm going to show you in the following table. So here's the table. And you can see that when 0.1 was plugged in, the answer was 0.2498, etc. Then successively you get to 0.249, 0.249, 0.249, 0.25, 0.25. And then for some reason, when the last two values were plugged in, the calculator, what it did is that it rounded somehow and got 0 as an answer. But it's obvious that as x approaches 0, the function approaches 1/4 or 0.25. Now, the interesting thing is that that's precisely what we have to find out algebraically in the next question, because the next question says, using algebra and the properties of limits, evaluate limit of the function as x approaches 0. So that's what we're going to do next. Now, notice that with this particular function, you can't really just plug in 0, because if you plug in 0 here, it becomes undefined. So we have to do something algebraically. So let's rewrite it over here. So they want us to find the limit as x approaches 0 of square root of x squared plus 4 minus 2 over x squared. So in these cases, what you normally do is that you want to get rid of this square root in order to find an expression where we can cancel out x squared. And what we have to do in this case is multiply by the conjugate. So the conjugate of this expression on the numerator would be x squared plus 4 plus 2. And then we also have to multiply it by the denominator. So this multiplied by x squared plus 4 plus 2. So then what are we going to get? We're going to get the limit as x approaches 0. Let's the here. Limit as x approaches 0 of, and this is just the difference of squares, so we're going to get x squared plus 4 minus 4, x squared plus 4 minus 4, a difference of squares, over x squared times, and I'm not going to expand this, I'm just going to leave the expression, x squared times square root of x squared plus 4 plus 2. So notice what's going to happen here. So 4 minus 4 will cancel out. This will be 0. And then x squared over x squared will be 1, right? So what we're left with really here is to find the limit as x approaches 0 of 1 over square root of x squared plus 4 plus 2. And notice that now if we plug in 0, the expression will not be undefined. So now we can just plug in 0, and this will equal 1 over square root of 0 squared plus 4 plus 2. And this is the same as 1 over square root of 4 plus 2, which is the same as 1/4. Very well. So what you're going to find next in your slides is exercise 12.1. And these exercises I'm sending together with this PowerPoint. They will have the solutions. So I would suggest you guys do these on your own. So questions 1 through 8 all have answers. The ones that don't have answers are 9 and 10 because you have to prove things. So I'm going to do these on this video. That way you guys can see one possible way of doing each of these questions. And let's start with number 9. So here they want us to show that this limit is equal to 1 over 2 square root of x. Okay. This one reminds me of the one that we did before in the examples. I'm still going to do it. I'm sure most of you guys, not everybody, would know how to do this anyway, but let's just do it. So the limit as h approaches 0 of the square root of x plus h minus the square root of x over h. Now, obviously, we cannot plug in 0 because then it becomes undefined. So in these cases, one would have to multiply by the conjugate. So square root of x plus h plus square root of x. And if we multiply the top, we also have to multiply the bottom, as you guys know. Okay, so this would give us then, and don't forget the notation, right? So we have to rewrite all this. So limit of the function as h approaches 0 for x plus h minus x, right? Because this is simply a difference of squares. And then below this, we're going to write h times the whole expression. We're not going to expand it or anything. X plus h plus square root of x. And obviously, these x's are going to cancel out. This is going to cancel out and become 1. And this is going to equal 1, or let's not forget, the limit as h approaches 0 of 1 divided by square root of x plus h plus the square root of x. And then we have finally arrived at our answer. Because if we plug in 0 here for h, we plug in 0 for h, we're going to get 1 over square root of x plus square root of x. And this evidently is 1 over 2 square root of x. Very well, so here we are on question number 10. And this will be the last question that we'll be doing on this video. Remember, you will have another video sent out to you this coming Wednesday. And on Friday, you will have a quiz evaluating you on limits and whatever we have left over from trigonometry. So in this case, they want us to show this limit and that we have to reach this final answer. So it's basically another algebraic question. In this case, we don't have to plug in the 0 because, again, it's going to become undefined. And what we need to do is manipulate this algebraically. So let's do that. Limit of the function as h approaches 0. And I'm going to start working on this as we go. So let's cross multiply, right? Let's go cross multiply this. So this would be x minus, and here it's important to use parentheses just to not forget to change certain signs. X plus h, and this divided by x times x plus h, and we still have this dividing h. Okay, so let's rewrite this here, limit as h approaches 0, but I want to do some operations here. Now notice that this negative here is going to change the sign, so this is going to be negative, and this is also going to be now negative. But x minus x cancels out, so I'm going to be left with minus h over x times x plus h. And what I always recommend is to not expand this until the very end, okay? And then we could rewrite this as this divided by h. Okay, now, because we're dividing this by h, we can rewrite this as the limit as h approaches 0 of minus h over h times x plus h. And we're finally getting to the answer, as you can see, because this and this can cancel out. This would be 1. And then if we plug in 0, we're going to get negative 1 over x squared.